It's a great pleasure to have here Mike Stadnisky and Seddon Thomas from Phitonex. We're very happy to host this webinar. Mike is going to be talking about these really exciting new fluorochromes that they've developed with a new technology, and you'll see how capable they are. And we're really excited that Mike will be presenting for the first time data on a 40+ color panel using some of these dyes. So we're really excited to hear all about this. Let me just start by introducing Mike and Seddon. Seddon will be taking questions along the webinar. So make sure to if you have any questions, to go to the chat function and just put your questions there. I believe maybe Seddon may interrupt during the webinar and ask these questions if they're pertinent at the time, or we'll leave it to the end and then Seddon will monitor that accordingly. So let me just introduce Mike and Seddon. So Mike is the CEO of Phitonex. He was a former VP and General Manager of Informatics at BD Life Sciences and former CEO of FlowJo. He led FlowJo in its transformation to become the leading single-cell informatics company, including bringing a gene expression analysis platform from an idea to scientists in just 9 months in a partnership with Illumina. So that was extremely exciting to see that develop. He's an author of 11 patents and was a finalist for the 2014 ISAC, or International Society for Advancement of Cytometry, President's Award. If you'd like to stalk Mike, you would be happy to know that he played Division I college rugby, and competed in Division I track in graduate school, and is an ultra marathoner, an avid long distance swimmer. So if you'd like to take that information and use it. So Seddon Thomas, she's currently a research application scientist at Phitonex. She earned her bachelor's in chemistry for Williams College and her PhD in medical sciences in immunology and virology from Harvard Medical School. She has over 20 years experience in flow cytometry and immunology research. During her graduate work at Harvard and postdoctoral training at the University of Chicago and NIH, she published 34 papers and received numerous honors, including the AAI Young Investigator Award, President's Rising Stars in Mucosal Immunology, and multiple NIH Fair Awards. So it's again a great pleasure to introduce you, and we're really looking forward for this webinar. Mike, thanks.
Great. Thank you, Rui. Share my screen here. Yeah, thank you, Rui. Thank you, Kat. This is a lot of fun, and we're going to definitely show some new things today. But I think I wanted to start off with a little bit of lightheartedness, which is, I think most of us have probably spent at least the past 3 months spending an exponential time looking at exponential graphs. And I thought that today really shouldn't be any different. So we're going to talk about the exponential graph that we live with in our field. And that exponential graph looks at the number of colors we've had over the years achieved. And really, we can think about this as a way of how we've started pushing the envelope in dyes and also in hardware, right? And so really, if you look at this, and I think Mario has coined this as he would his own law of flow cytometry, and that the number of colors doubles every 10 years. And this actually shows everything that was projected dyes in development before we started developing dyes, right? So this was the potential for the Brilliant Blue series to go on, although I think we've seen that it's limited down here. But I think another way to look at this plot, because I think we're all very familiar with this, is in looking at dyes and actually the fact that they do drive hardware development. There was you get a big push of dyes, and it would be a leapfrog moment, and then that would lead to the development, for instance, of when we had the first several organic dyes in the 12-color Fax Vantage. Then we got the Q dots, which really pushed the development of an 18-color LSR2, and then recently we had the Brilliant dyes, which really pushed us into the world where we had the Fax Symphony, really one of the first high-parameter flow cytometry, sort of conventional flow cytometers. I would also argue that when we get this pushing, we also get this drive towards democratization, where you have instruments of the Cytoflex or the Attune, which can come in at lower or lower or mid-end number of colors, and really democratize doing flow cytometry with that number of colors. However, we're in a really interesting spot, and the past couple of years have taken us here, where we're in what I'm calling an inversion, where all of a sudden we've sort of had this leapfrogging because of spectral cytometry, or you have the Aurora with 64 detectors, or you have the ID 7000 with 188 detectors, and you have them putting out press releases saying that we can get to 40 colors or we can get to 44 colors, and really showing some high-level analysis, and we'll dive a little bit deeper in on that today. But the real key here is we have entered this point where we're living in an over-detectored environment, right? So we have the capacity to ask many, many more questions per cell, but we're really limited, right? We're really limited to really practically into this 28 to low 30s number of colors that we can answer really cleanly, and thinking about how easy can we make experimental design, and is the data itself actually analyzable, the population resolve, something that we'll spend quite a bit of time talking about today. So this talk was presumably titled Introduction to NovaFluors, although I added some subtitles here because it's a bit more, and it's actually quite a bit more, because I'll be showing you essentially the last 2/3 of this presentation are entirely new data for some data that we are just publishing today with a white paper, and then also sharing the actual raw data and the analysis. So we'll lead you through all of that, and in the case that you want to dive deeper into this, we've got Stadin, who performed really the majority of this experiment, and we'll also have the data so that you can analyze it yourself, because as we'll see, there's a lot to discover in this data set when you can actually leverage the spectral clarity of these NovaFluors. But I thought worthwhile in the first part, just let's take a step back and talk about the technology. Let's talk about the technology platform, and we'll think about it from a design point of view and sort of take, if you will, flow cytometry panel design back down to the studs. And I think the way we do that is we think about, okay, what's all the things we have to think about when we're thinking around flow cytometry panel design, which we know can take months and months and months, right? And to give you kind of a little bit more insight, right, we were able to take this data I'll show you later. We were really able to take a backbone panel of, really, we ended up being 34 colors, add our 6 NovaFluor labels in, run it, analyze it. And we did that in really under about 2 months, right? And so, but all the things you have to consider are spectral overlap, right? As I've said, you know, our labels lead a decidedly more colorful life than we want them to. We have to think about antigen density and how we map that to brightness. We have fixed brightness, so we have to deal with PE and sort of PE conjugates, as we'll discuss, because that's just the brightness that we get. We have spillover spreading, another area that we'll spend an enormous amount of time on, right? And spillover, you know, I think it's pernicious in the sense that spectral cytometry doesn't get us away from having spillover, right? There's no magic there. We still have a lot of spill, and it really complicates our data analysis. So that's something we're going to spend a lot of time on today, because it's something we've thought a lot around. How do we get around, or how do we get to the point where we have very, very limited spillover? And again, we'll quantify that both for our labels and how they perform, but then also how they perform in panels. And then also this notion of staining index, or we'll talk about separation index, which, you know, I think is a really objective way of thinking about, well, what is brightness, right? And to us, brightness is the ability to resolve a cell population. And so really it should just be not just staining index, but you should also think about, well, you know, what about the width of the negative population? This is something we'll spend a little bit of time on. But if we take one step back from all the 4 different things that we're talking about here with panel design, we got to ask the question, which is, how does underlying dye performance influence all of this? And the answer is, well, it influences certainly 3 out of 4, and it also influences the fact that we're stuck with antigen density with fixed brightness dyes, right? So we're essentially driving on old highways with current dye technology, and all of these are having to accommodate the dyes rather than thinking around, hey, what if we have fluorescence that was built for biology, right? And so to drive a little bit deeper in on that, I'm gonna kind of focus us in terms of certain laser lines. I'm not gonna talk about DUV today. There's no labels that are dated. I'm not going to talk about the IR today because there's very, very few lasers that are out there in the world with that. And then in the middle, we will spend quite a bit of time, you know, speaking about these 5 lasers, but the impact of our labels on them. And we'll particularly focus in on labels that are excited off of the blue and yellow green, which I'll refer to as BYG, right? Because it is really the notorious BYG. I know this is a New York group, so I had to get a shout out in there. So the first thing is, why do we focus in on the BYG labels? So the simplest way to think about this, and we'll dive into some of the spectral data, is, you know, let's look at some labels that have a primary laser, so for instance, Per-CP or brilliant blue, that's excited off the blue, and then what are they cross-excited by? And we see, for instance, that Per-CP and the brilliant blues are excited by violet. They're also excited by yellow-green. P and the PE tams, as well as the tomato, are cross-excited off of the blue, right? And so we have these labels that are in that space where there really has not been a whole lot of technological advances, yet almost every instrument has a blue and a yellow or green laser, right? So we think about an LSR for tester, we think about a tune instrument. All of them have these lasers on board. So how can we think about attacking those laser lines? And again, just to put this in context, I'm showing here a ribbon plot from the Cytec Aurora SpectraFlow software. And the way that these plots work, you look at this primary detector here. I would say put a note in that, right? This is the detector, which presumably you have peak fluorescence, but I think it's more important to think about in terms of what is the primary detector for that. But really everywhere else, even though it is a signature, you're still getting the introduction spread, right? And so these are, this is off a blue excited dye. So if we look at the blue excited dyes and dive a little bit deeper in on that, we look at something like PerCP, right? We certainly have a primary detector that's in the blue, but a huge amount of spread, and also you can call it signature as well, into the yellow, green, into the red. Brilliant blue, and I think we'll see a lot of this when we start looking at the other brilliant blue dyes that we've looked at and other people have done performance testing on. They're really notably quite loud in the violet, and they add a huge amount of spread into the violet, an area that you'd really like to leverage using some of the brilliant violet dyes or the BUV dyes, to drive more of your high parameter panels. But it's difficult because now you're increasing the difficulty of data analysis and experimental design by adding so much spread there. And similar story for Brilliant Blue 700, where there's a huge amount of fluorescence into the violet. And so let's just take it all the way down and say, what if you could start from scratch, right? And this is the thing that honestly gets me really excited about what we can do, which is, what if you could design a fluorescent label like you would design, for instance, a piece of software, or you would design, really anything. And then given that, what would the implication be for panel design? And could you make experimental design as well as analysis much, much easier? And there are three key requirements. And a lot of these actually came out of some amazing conversations we had at Cyto. And then since then, last year, when we sort of launched this as hey, look, we have this technology, we really want to get it into your hands. And the three requirements came really screaming clear to us. And the first one was bright and clean. Pretty much the most obvious one, right? I want it to, emit only where I want it to. I don't want it to be cross-excited, right? And really, signatures are the result of really poor dye performance. I really want to just multiplex and just hit each detector so that I can do high parameter flow cytometry, really any parameter flow cytometry easily. So limit that cross-excitation. Got it. The second one that was, and I'm going to skip over it for a moment. The second one that was interesting for people was, hey, could I control brightness? Could you give me a volume knob on brightness? Because I don't want to just have, for instance, fixed PE Sci 5. I'd really like to be able to control that and choose a color, right? And then amp that on. Maybe I could even think about simultaneous low antigen detection, right? On single cell. And the emergent one that was really interesting for us as we learn more about both the current tandems and the way people are working with current polymer dyes is this notion of consistency and stability. So this is another area where I'm going to show some brand new data in terms of what does that look like in terms of consistency, but can you make these stable, right? And for what it's worth, there's no special buffers that are needed for the labels that I'll show you, right? And we'll actually really push that idea of like, what is the notion of consistency and lot variability, and just how stable can we push this platform? So these will be the three requirements that we'll design on top of. How are we going to attack all that? We have a technology platform where we actually take single-stranded oligonucleotides and bind them onto component organic dyes, small organic dyes. And then we can actually anneal these, we can construct and synthesize this phyton structure. This is an artificial cruciform structure, right? For its worth, it's really not recognized by nucleases because it is so artificial. And what this enables us to do is engineer down to the sub-nanometer level the way that dyes can interact on the platform. And you'll see that that gives us some really interesting capabilities when it comes to spectral clarity. And for what it's worth too, we call each one of these arms of the cruciform a cluster. So we'll talk about two cluster dyes, right, which are two cluster labels, which have dyes on two arms. We'll talk about four cluster, and this is what enables us to tune the brightness up. And what we can do is actually hang a single-stranded oligo off the end of this and use that to conjugate it to antibodies, something else I'll describe at the end. The capabilities that this gives us are, one, actually, if you think about it in terms of, well, can you manufacture this, is you can manufacture this because there's just standard oligo manufacturing, right, that you have. And so I'll actually show you some consistency results on that and also discuss what that even looks like in flow cytometry. The other part of this is that it gives us the capability to do tunable excitation and emission. I'll show you what that means in a second, but even if we focus in on the blue and yellow green for a moment, instead of having those be sort of convoluted where you buy a 5-laser instrument and all of a sudden, the second you run an experiment, it's a 4.5 or 4.25 laser instrument, you can think about those laser lines independently, right? And the second part of this is tunable brightness, right? What if we could actually tune brightness up and down and do it Let's talk about that. We've also done some work in tunable signatures for what it's worth. There's a lot of biology, I think, standing between us and the ability to use those tunable signatures, but we actually have, we've proven out actually the ability to actually create tunable signature dyes. Okay, so we're gonna focus on these one at a time. I'm gonna take you through some data on each one of these. And again, there'll be some new data sprinkled throughout this, particularly in the middle. The bright and clean part is a really interesting one. And so I'm showing here the spectra of our plot. This is this notion of tunable excitation and emission. And if you look at the way that we've engineered these dyes, for instance, the first 6 dyes that we've done, 3 off the blue and 3 off the yellow line. For what it's worth, the nomenclature of these things is actually is quite simple as well. This is where it's excited, right, which is off the blue, or it's off the yellow line, and its emission is actually this number here, right? So another kind of nice thing for experimental design is you know exactly where it's excited. Remember, look independently, and then where is it going to emit? And so you can see what we've done first, if you look at just the dotted lines here, is we've separated the excitation of the blue and the yellow lines. So you can begin stacking these labels, right? And that'll become important certainly for a high parameter work, but it's important on any instrument because now you can say, okay, well, I don't have to use PE tandems anymore. I can just use these and immediately upgrade the amount of questions I can ask per cell using these labels. The other thing you can see is we've actually stepped the Stokes shift along of these labels, right? And we're getting very, very low cross excitation. And I'll actually show you what that looks like again in panel design in a moment. But the point is now we can use all 6 of these independently. If you're wondering, well, how do I get access to begin thinking about experimental design for these labels, we took the spectral data and actually published it up on an open source spectral viewer called FPBase. So that's there and gives you a sense of the type of clean fluorescence that we've got. The folks at Cytec were also kind enough to take our labels and post them up on their Cytec full spectrum viewer. We're working with a number of other companies to get it up on their spectral viewer to be able to enable people to get this to be deeper into their panel design. But I think this gives you a sense, and you will gives you a preview of what's to come, which is that we're able to hit these detectors very, very cleanly and stack those laser lines. And notably, they're incredibly quiet in the violet.
All right, Mike, I just want to interrupt you real quick to remind everyone, please feel free to ask any questions. I can answer that in the chat, or I'll interrupt Mike every once in a while with the questions that you have. So.
Yeah, please bring it. Great, thanks, Ed. So this is actually just taking a look at our dyes, and this is for what it's worth. This is on an Attune. There's no special laser powers that are being used. We're using the default settings here, and in fact, for everything that you'll see, we were using the default gain settings. And so what you can see here is, for instance, this Nova Blue dye is really almost like a fantasy blue dye, right? It only emits where we want it to emit in this blue 1 channel and has absolutely 0 fluorescence anywhere else. We've got this Nova Blue 610 dye, 660, again, a really clean dye, 570, 610, and then 660 off the Nova Yellow. And we'll show you how those perform, again, in panels in a moment. This is just looking at them on beads. But it gives you a sense of the cleanliness across the spectrum, at least, and in not just an Aurora instrument. I think another thing, that we need to think about too is that, this major problem of both PE and PE tandems, these dyes are excited both off of the blue and the yellow-green lasers as indicated here. So what we've done here is actually taken the typical filter sets off an Attune or an LSR Fortessa and the recommendations from those manufacturers, right? And you can see, for instance, you've got this overlap of PE being in both blue 1 and yellow 1. You've got PE Texas Red showing up in both spots. PE Dazzle, which is sort of the problem child of PE dyes, as we'll discuss, being recommended for 2 different channels. And instead of having to run one of these labels and forsaking, and getting rid of essentially several of your channels because of this amount of cross excitation, now you can begin thinking about stacking these labels. And so Seddon's actually taking on some work now to show what panel design could look like on an LSR Fortessa. But you get a sense of this just even looking at our data off of the Attune, is that now you're able to leverage the entire detector array off of these labels. So here's an example. We're going to choose PE Dazzle, right, which is a great dye in the sense of it being bright, but it's a bad dye in the case of what's the cost of doing business. The cost of doing business with PE Dazzle is really the ability to not use many of your detectors off of either the blue or the yellow green, depending on where you're going to detect it. So here's a PE Dazzle, and this is its emission, right? And it's being incredibly cross-excited, right, off of nearly every line, right, that we're looking at in the BYG. And so it really inhibits your ability to leverage both the blue and then the yellow or green lines independently. And what we've done is said, okay, look, we're going to use Nova Blue 610 and Nova Yellow 610, and they're going to be independently excited. So now you can use both of those detectors, right? And that's just one dye example, right? And I think it gives you a sense of also what we intend to do to build out laser lines and do this cleanly, right? Because it's not only just PE allows us cross excitation, it's also the spread that this and other labels were introduced into other channels. And I think a great plot that shows kind of how these things perform is actually maybe the simplest one that I'll show, right? And what this is actually some compensated data from all 6 of our labels, right? So this is put together by Ian and Flojo, and grateful for him putting together these high resolution plots for us. But I think what's important to note here is it sort of reveals to you a couple different things when you're looking at this compensation data. Is that one, you're getting, you're essentially getting this beautifully perfect compensation which you expect, right? The medians of the negatives and the positive are right on. But I think there's another thing to note here, which is note the lack of spread, right? There's no trumpet effect that you're getting in terms of spectral spreading of these labels even after compensation. So you are getting very, very clean fluorescence, right? Maybe we should say, we're making quad gates great again, right? And it's really amazing because you're actually able to resolve these populations quite a bit better, right? Just looking, for instance, at these compensation controls. So I think it's a powerful way of thinking about all 6 of these labels, is that we really are thinking around the notion of high resolution biology, which means your ability to actually analyze the data that comes out the back end, detect mid populations, really think around the dynamic range that's in the biology and leverage fluorescence to detect that.
Okay, Mike, we've got a few questions. Just thought I'd interrupt you with. So one question is, around the stability of the dyes and how susceptible are they, for instance, to DNase, other things like that.
Great, yeah. So we'll touch on we'll touch on temperature stability and also fixative stability in a moment. But we have done DNase testing, and it's not affected by DNase. So there's no loss of signal there. So they're not susceptible to that, right? And it's thought that the nuclease really can't bind on to cleave. We haven't run the physics on that, but it's more important to say that the effect of that, later on is we don't see an effect.
Okay.
But I'll touch on stability actually in 2 slides.
Yeah. Okay. And then there's a question around whether they're tandems. So just understand how that works.
Yeah, this gets interesting, and I had an email about it this morning in terms of people asking around tandem stability. They themselves, the labels themselves are not tandems. But there is fret that is occurring on the platform, right? So they don't have the same type of tandem issues either in terms of their instability or in terms of the fact that when you conjugate them on an antibody, the fluorescence can change. Because if you think about it, we fixed the fret interaction. So we don't call them tandems because it is, but there is a fret interaction that occurs on the DNA platform. But the dyes are fixed in position because that's exactly what we're doing on the DNA platform. So we're saying you're going to be at that, in between the dyes, you're going to be at that position, you're going to be at that position, right? And that's, if you will, that's sort of the, that's the magic of the secret sauce, is actually controlling the geometry to get the type of excitation and emission that you're seeing here. But it's incredibly stable, both in terms of you can put it on any antibody and the fluorescence is going to be exactly the same, which I think has important impact on compensation because it doesn't mean that you have to have your specific tandem dye be that compensation control. But I'll also show you lot-to-lot consistency as well, which shows you that we're able to do that and do that incredibly consistently. So hopefully that answers your question.
Right. And there's another question. Are there any aggregate problems like there are with the brilliant dyes?
Yeah, good question. We've never seen anything like that. And so the thought there is actually because the DNA platform that I showed, although we laid it out to be flat, and it's about 20 nanometers if you lay it out flat, it's actually quite a bit less than that because the DNA actually has this cup-like structure which behaves like a solubility cage, right? And so what we've never seen aggregates in solution. And really we think it's because of that DNA structure. The other thing that I'll add is, we're able to control the degree of labeling. So there's one DNA on one antibody, or 2 phitons on one antibody. That's a pretty small structure, right? It's much smaller than PE, and and quite a bit smaller. And so just it's smaller than PE on an antibody, right? And so we don't see those aggregates. And in fact, I'll show you some of the stability data that shows, in fact, some of the, if you will, the proof that there is this solubility cage. But no, we've never seen aggregates. And we've stored labels for months, for instance, and then QC them again on cells.
Okay. Yeah, so I think, and there's another question, just is the label to the antibody on the FC portion, which that is where it is. So
yes, and in fact, so let me add one more piece to that, which is that, we worked with a partner on a conjugation kit that I'll talk about later, with really two aims. But they've tested thousands of different conjugations using the chemistry that we're using, and they have never seen any interference with the antibody specificity, right, or its ability to bind onto targets, right? So we are targeting the FC region of the antibody. The other part of that, though, because I think my joke is always like, I'd rather buy a 6-pack than a homebrew kit, is we also wanted to make the conjugation kit quite easy to do. So I'll show you later. It's 3 steps, and you can go from not having, from essentially having unlabeled antibody to conjugated antibody with these 6 labels in a day. So, we'll talk about that chemistry in a bit.
I think I'll let you go ahead for a bit and probably interrupt you a little bit later. So
sweet, thanks, Ed. Mm-hmm. Cool. So yeah, so I'm going to touch on what's brightness, right? Like that maybe that'll be the question I would ask of any fluor, right? And so people always ask, they say, well, how bright is it? And for me, brightness means the ability to separate biological populations, because it should account for the ability to actually separate a population from the negative, right? And so this is some data that came out of the NIH. We got them 2 of our labels, it's NovaBlue 610 and NovaUO 610. We looked at actually separation index in this case. And the reason that we did that is because it also looks, if you look at the calculation, you're also looking at this versus the 84th percentile of the negative. And I think that's really important, because the separation index is really should be thinking around, well, how can I get this away from background, right? Not just, okay, now I'm able to, for instance, I'm able to do 2 logs of change, but I have a huge amount of background, right? And so as it turns out, both of these labels actually have the same separation index as APC. And for what it's worth, this is in a 2-cluster format. In other words, off of the cruciform arm, they have these Fred interactions occurring on 2 of the 4 arms. And hold that thought for tunable brightness. So the second one, and there was a great question in there, which you could have used as a segue. I can't help but lean when I say that, to talk about consistency and stability. And this was definitely something where exactly the person asked that question exactly. I think there was a lot of questions around how stable are these? The aggregate question is another one. Do I have to use any special buffers? Do I have to incubate? Are there any time incubation-like questions? Like I have to do this right before, 15 minutes before I do my experiment. And I'd say we went a very different way, which is just how stable is this platform? And can we make lot-to-lot variability, essentially a thing of the past, which I know sounds like a lofty goal, but why would we not try and set that bar? And so the first test here, and we actually tested this out to 3 weeks here, is we just literally left our labels on a bench, right? Not something that we recommend, but one, it happens, right? Something we call this like sort of like a graduate student experiment where you're like, ooh, the new graduate student left the labels on the bench. There's no change in fluorescence for up to 3 weeks. But the other part of this was for, sort of high throughput use, right? Where you're running, over either a day or several days, and, you're seeing drift in the underlying fluorescence there. Honestly, you're just not going to see that with these labels, right? So you've got up to 3 weeks, absolutely no change in the fluorescence. The second experiment was, hey, how can we push that harder, right? And so what we did is we took, PBMCs and stained them with this anti-CD3, and then we fixed them for 2 weeks, right? So 1%, PFA solution, and then compared that to fresh, right? So just literally left them. And it turns out there's actually no change in the fluorescence, right? So this is really pushing, the ability for us to say, hey, look, you could run that experiment and fix it, and then you've got to come back in the lab 2 weeks later, right? We didn't realize that this was going to be relevant to sort of our current operating modality, where you might have to go in and stain and then wait a little while and then come back a couple weeks later and run it. But the point is that you will not see differences there. I'm gonna anticipate a question, which is, have you tested methanol fixation? Not yet. Hold that thought, right? That's another test that we have to do. But the other thing, and this is some brand new data, so let me kind of set it up here, is this notion of lot-to-lot consistency, right? And so what does that mean? Like, how do we think about that and break that apart? So the first one is manufacturing, right? So you've got to manufacture these oligo-based labels, right? So we do that using an ISO 9001 certified lab, right? As you'd expect, right? And then we bring them in and we assemble them into these cruciform structures. And then the other thing that we do is, so we test those cruciform structures, but every lot of labels that we ship out, we QC on cells every single time. So we QC on PBMCs every single lot. And the reason is honestly, some of our frustrations with, as you expected, we've been doing some of these higher parameter studies. We've been purchasing a lot of antibodies. And, we like seeing data that says, hey, this is your label on an antibody that you purchased on cells, right? Not on a cell line, not on something else. And so that's the way we think about this, thinking around lot to lot. And so two pieces of data here, one that I'm showing here. What we're looking at here is actually spectral comparisons across all 6 labels. And this is comparing 2 different lots, right? And so you can see that essentially, off of these, the 610 and 660 for both yellow and for blue, there's in essence 0% differences in between the lots, and there's less than 5% off of this Nova Blue 530. So the goal is to have less than 5% lot-to-lot variability. So if you're thinking about, well, can I use these labels and can I use them in a longitudinal experiment? The answer is yes. And you don't need to go and hopefully think around, oh, I need to purchase a gallon of this because of a lot-to-lot variability. But the other thing too is, what about flow? And the answer is, when you look at flow and the way we're manufacturing these, the CV of the MFIs of all of our labels really range from 2 to 4% on flow. So it's an incredibly consistent manufacturing process that we have to make these labels.
Okay, Mike,
so hopefully I've addressed.
Yeah,
let's do it.
Some great questions here. One is about the phyton structure, and how big is that, and is it can you use it for intracellular staining?
Yeah. So I mentioned it's 20 nanometers across. Actually, quite a bit smaller than that. It's 150 kilodaltons in size. And so have we tested intracellular? No. Seton's actually playing those experiments right now. And so, working on, okay, well, which intracellular targets should we be going after? So I would love it if you could say, hey, look, these are the type of intracellular targets that we're interested in, because we're quite literally planning out those experiments right now. We certainly have some targets in mind, but would love to hear from you about, okay, what's of interest, and is there a way for us to work together on that?
Another question, how stable are the conjugation kits, and are we planning on selling directly conjugated antibodies?
Like, definitely the latter being my most favorite question. Let me answer the first one. So we've tested conjugates that we've made, gosh, out to several months, and I don't know the number of months that we've tested on the conjugated labels that we've had. I think the longest we've tested is 2 or 3 months for those conjugated materials, where we've leveraged this oligo-oligo interaction. And haven't looked beyond that. We've also tested mixes of them to see if there was any exchange in solution, and haven't seen that. We have to do some longer testing, but I mean, transparently, we haven't been around long enough to do, like, we tested it for a year, because we were manufacturing at scale up until 3 or 4 months ago. Do you have plans to sell conjugated antibodies? Yes. And so I don't have anything concrete to say about that now. What I will say is, if there are antibodies that are of particular interest to you on particular labels, we are already, sort of essentially taking orders to say, okay, I would like 1 milligram of CD45 on Nova Yellow 660. So we're happy to work with you on it to get that level of that kind of thing into your hands now. Having actually off-the-shelf conjugated antibodies is going to take us some time. So I don't have anything I can commit to right now, but it's definitely our intent.
Okay. And the last question, I think, is more probably future looking, but interested in whether we use this in image cytometry or fluorescence microscopy. Yeah.
So we have a couple of people who are pulling us into that quite literally right now, both certainly in imaging. And I think that'll give us a good indication of what that's going to look like in image cytometry. I think we've got a lot of questions to ask around intracellular compartments, how they're going to perform and behave in there. And so I think, our first step would be, let's do all the intracellular tests that we need to first. And then, we're going to have some partners testing this in imaging as well. And then I think we have a really interesting story for imaging cytometry, because I think, as you're seeing, you'd really want 2 different things in there. You really want very high brightness in some cases, right? If you had very, very low molecule number, but it's that spectral clarity that could be really, I think, critical for, some of the imaging applications or image cytometry applications.
Yeah. And last one is around next-gen sequencing. Would they interfere with that process, or can they be used in some way around that?
Yeah, good question. Yeah, so there's been some really interesting interest in binding these on, for instance, like the total-seq antibodies or the ab-seq antibodies, right? Because you can hang an oligo off the end of these phitons and actually conjugate it directly to a total-seq or ab-seq, which, for what it's worth, is how we started. with getting these into flow cytometry at all. I'd say we are, the current conjugation kit, we're looking into strategies there where you could sequence them. And we've chosen sequences actually, to actually answer your question directly, we've chosen sequences for our antibodies and the way they're conjugating to, our phytons, the way they're conjugating to an antibody that are unique and will not be picked up as something else, right? They won't be picked up by, or they will not conjugate to, some mRNA that's in your cell, right? So they do have a unique sequence, and so you'd actually be able to pull those apart, in your NGS experiment.
All right, so I'll let you get back to the talk, and I'll interrupt you again.
Thank you. All right, last one, controllable brightness, at least in terms of the requirements, and then we get to some even more fun stuff. So I've talked about this notion of clusters with these arms off of this phytone structure, and so what I've actually been showing you is data off of these 2 cluster labels. And so what we'll show you, I'll actually show you how we went from 1 to 2 clusters, and the fact that we're able to replicate these 404 networks. And then I'll also mention how we're able to tune brightness, if you will, all the way up to 11 with our 4 cluster label. So the first one is the good science experiment. So if you think about this phyton structure, it's essentially symmetric right along this y equals x-axis along this diagonal. And so what we did was first was the good fluorescence experiment, which is we were able to replicate that experiment. For the fluorescence geeks in the room, this actually gives you, and this is a really great way to think around, okay, this is a tandem. It's really, it's the threat that's on the platform. And remember, because the Fred equation scales with the square of distance, you can actually see that, for instance, if you get smaller changes, for instance, if you're on another part of the arm and you're able to make that, tune that distance, which is exactly what we're able to do on platform, you can actually get a more efficient transfer of energy in that Fred interaction. So obviously a very marginal difference here, right? But I think really interesting when you think about, okay, well, what's actually occurring on the platform? But this replication enables tunable brightness. In fact, we can get it to be stoichiometrically twice as bright. Now, I know this is a spec plot, so, of course, what I said and what you're saying right now is, look, show me the flow. Okay, let's do that. So we took a 1 cluster versus a 2 cluster NovaBlue 610 label. Good science, we did the fluorescence -1, or the way I always like to think about it is fluorescence minus outcome, right? Label only, we just doped in the 1 cluster and the 2 cluster phitons here. So you can see the background's very, very low. And then we can compare the 1 and 2 cluster NovaBlue 610s. And I think there's some important points to make here, right? We are seeing that it is in fact twice as bright, right? If you look at that in histogram. But I think there's another important piece of this, which is that we're actually able to increase the separation index, right? We have not appreciably added to the background at all, right? So we're quite literally able to tune in the separation index and make a brighter dye without the compromises of adding to the background. I think that's a really important point to make. We're thinking about this in addition to the spectral clarity. So we pushed that even harder. So we actually took our highest performing separation index dye, which is this Nova Yellow 610 label, and took it all the way up to 4 clusters, right? And so it is, in fact, when you look at it on the spec plot, 1.9 times as bright, right? This is a normalized result that shows it has less spillover, not as relevant as the fact that it is, in fact, we are able to go now up to, if you will, 4x. And so what we did is then compare this and try to get a handle on, well, just how bright is it? And so we're using MFI as a proxy here of brightness. And so here what we're looking at, again, we're not looking in, this isn't PE's primary channel, this is in the Nova Yellow 610 primary channel, is we do get on a flow cytometer, get 1.84 times as bright. So we're able to stoichiometrically control that brightness. And we're saying it exhibits PE-like brightness because, again, the separation index is really excellent, right? And we're able to tune that separation index up. But I think what's important to look at too is what's occurring even in the next adjacent channel. And the answer is not a lot of fluorescence, right? And I think that's what really distinguishes this from PE. We can think about not only tuning brightness on a per color basis, but doing it across multiple labels at the same time. And so what's this being pulled into? Small particle and extracellular vesicle detection. There's a lot of interest in looking at this 4 cluster Nova Yellow 610 and triggering off fluorescence because we have this very high and also very clean signal. P and P conjugate replacement for these undetectable drug targets. Checkpoint inhibitor simultaneous detection is this node of essentially multiplexing across multiple colors. And then an emergent one for us actually is, hey, can we get this on this very clean, also very bright thing onto, looking at ACE2. So hopefully I've shown you those 3. Maybe Seddon, we could take take just like a quick, like, do we have questions that I should handle now before we, if you will, jump off at the deep end?
No, I think you actually covered a lot of questions. We've had a lot of great questions, but.
Awesome. Keep it coming, particularly because we're going to light it up. So now we're going to talk around 40 color data. So this is all brand new, all of it. We talked a little bit about panel design and how we got here last week, but all the analysis you're going to see and some of the derivative analysis, both in terms of panel design and some of the more advanced stuff that we did, all brand new. So keep the questions coming. Okay, so where did we start with this? We really wanted to test this thesis that we had. We talked a ton around panel design. We talked around spectral clarity. We talked around spread. Okay, great. Proof's in the pudding, right? Do something in terms of panel design, you know, that essentially no one's seen before. And so, okay, let's do that. So what we did is we took this SciTech panel. So they have a white paper where they published this 35 color panel, and they've shown some of their analysis results, you know, online. And so we took this and really looking at what was commercially available, you know, really takes it back down to essentially a 34 color backbone panel. And so we started with that 34 color backbone panel. And what we did is actually drop in, so and for what it's worth, this is the only reagent that wasn't commercially available for us, so we put CD19 on one of our labels. And what we did is literally plug and play our 6 labels. The 6 labels we've been talking about in their 2-cluster format, right, on 6 different antigens. And I think what's important to note here is, yes, some of them are high antigen density, right, like a CD19, but we also went after a lot of chemokine receptors, right, or CD40, where these are not, you know, depending on the immune state or depending on the cell, they're not all CD4, right? They're not all high antigen density markers. And it led us to a number of different observations about, one, panel design sort of at this level, but 2, really how do these perform now in when you're really trying to push the envelope here. We created this 40 color panel. The first one is an first plot's an incredibly busy plot. Hopefully they'll all be a lot more clear than this, but it gives you a sense, and if you will, preview of what's to come in terms of thinking around the performance of these labels in this panel, which is that, you know, we are hitting the detectors incredibly clean, right? So we can literally plug and play these in. We've got some recommendations around how to do that to drive this kind of number of questions. But the first thing that I think is really worth looking at when we sort of dive into this panel is what's the similarity matrix. So this is a metric that you can generate, right, using the SciTech Full Spectrum Viewer, looking at the similarity of different dyes. And so this is looking at a similarity, you know, index of every single label that we've put into this 40 color experiment. What we found is that, you know, the similarity index scores really between 0.8 and 1 are really the most critical when you're thinking around, okay, can these really be used together, right? And that's thinking around the spectrum of the dye and how similar are they, will I be able to actually deconvolute and separate these, right, and do some biology with these labels. And so this view, you know, I've laid this out by laser here, and I think you can start seeing some of the interactions that are going on. But I mean, you guys know some of my background. I had to cluster it. And so I clustered it, and this actually gives us a really interesting view on what are the clusters of similar dyes, and also what did we see when we were running this experiment. So I had to hierarchically cluster it, so that's exactly what I did, and I'll pick out some of the insights from the high parameter panel design as we get through this. And so the first one is one that you would probably expect, which is that we had a lot of similarity in the violet, and we actually saw these violet dyes really displaying a bunching effect when we looked at IgB-BV480 or the CD3-BV510, right? And again, we're sharing this data. So if this is one of those Lamar Burton reading rainbow moments, if I'm aging myself, I don't care, where don't take my word for it, we're going to give you the data, and I'll show you the links at the very end. But you can see that we do get violet, you know, that are very violet dyes that are very, very similar, right? Notably the super bright 436, right? And E44 450. The second one is I think an important point, one that you may have anticipated as well, is what's going on with blue, which is that, you know, brilliant blue and FCCF on mixing is very challenging. Those dyes are very similar. They don't exhibit a lot of signature type characteristics. And frankly, NovaBlue 530 makes it worse. And so if you're thinking about, well, how do I get less similar dyes that I can, again, deconvolute for easier analysis, but then also lower the complexity of my panel, we actually recommend that you use NovaBlue with either BB515 or FCCF, right? So you use those two dyes together, because you're lowering the complexity of your panel design. You're getting rid of these very, very similar dyes. And so, you know, at least in our observations, and we've got a whole bunch of supplemental data, which set and generated looking at Brilliant Blue 515 and FCCF, we really recommend, hey, look, drop one of those out and add in the NovaBlue 530, and you're just going to be able to do more biology off of the blue. right? The other one is PE dazzle. I mean, I've previewed this already. That's exactly as expected. This is sort of the problem child V, right, where PE dazzles is very similar to these other labels. But PE and PE dazzle are performing exactly as you'd expect, right? And we'll talk about that in the notion of, okay, well, where's spread being added in a moment. And the final one is a recommendation around really like the notion of PE Sci5, right? And really, I think it's time to sort of just shove off PE Sci5 and really should just be replacing that with NovaFluors 660. Certainly in these experiments, but I would also add, why not replace them, in conventional cytometry, right? So another thing that was worth looking at was, and we'll get into spillover spreading in a minute, is what's the desired, if you will, versus the versus actually where a label is actually detected. So we're just going to focus in on the BYG space for a moment. And I think this is kind of an interesting way of looking at, okay, well, where's that primary fluorescence? Where is it actually being detected? Because if you will, we sort of have a mixed system here. We've got the traditional dyes, which have a signature, right? But they do certainly have a peak of fluorescence or several peaks. And then we've got these incredibly clean dyes that are, if you will, sort of pinging the detector. So what does that look like in terms of how you're organizing this on a per detector basis? And so what we found, actually, when we just take a look at the backbone 34 color, is you've got per CP, that certainly has its primary detector, right? Its peak fluorescence in the blue. But in fact, what you're seeing is it's actually picked up by YG5. And so that this actually shows you, for instance, when you run compensation, you say, okay, what is the primary detector? It's the actual is actually what's being picked up in this YG5. So we'll use this visualization to show you what we did, because one of the experiment that we did to just sort of do the good science of panel design is set and took the 34 color backbone panel and dropped in each one of our labels one at a time. And that enabled us to look at, well, what does primary detection look like? And then it also enables us to look at, well, what does the spillover spreading differences look like? And so the first thing is, we drop in NovaBlue 530, and it goes essentially where you would expect it to go, right, into a detector in the blue. So very little change in detection of labels there. We drop in NovaBlue 610, again, similarly, no change. It's detected exactly where it should. It's hitting that B6 detector right on. Kind of same thing for NovaBlue 660, right? And we expect it to be in the B7, it hits B8, right? And no changes really anywhere else. All three of the blue dyes are hitting the detectors, and if you will, pinging those detectors and really adding into this panel. Now interesting things occur because you have NovaYellow 610, which we put on CD19, and because it is hitting YG1 so cleanly, it effectively grabs the YG1 channel and pushes PE into the blue, right? And so it actually takes the YG1 channel as its primary detector, and now you've got PE now being detected in the blue, right? So we've got a similar story for NovaYellow 610, which is detected in YG3, right? And what we can actually do is then push PE dazzle into the blue, right? And so this enables you, of course, to then do higher multiplexing, right? Because you can actually use all of these labels together, as I'll show you, but you do have to have some thought towards, okay, what amount of spread am I adding, and do I need to put those on separate populations? And then finally, this NovaYellow 660 dye, which is detected again, it's hitting the YG detector as we'd expect, and then again, pushing PE Sci5 into the blue, right? So these labels are so honestly clean and also quite bright enough that they're hitting their primary detector off of the Cytec Aurora and essentially pushing these PE and PE conjugates to be detected, at least in terms of their primary detection, into the blue. So if you will, all together now, you can actually see, right, that particularly in the yellow, right, we're claiming a lot of this yellow space, pushing the PE conjugates into the blue, and then we're able to stack our other blue labels on top of it. So what does this look like? So now let's talk about, that's just detection. These are signature dyes. Let's talk about spread too, and spread performance. So what we did is look at a spillover spreading matrix actually of the 34 color backbone, and now we'll build on top of that, right? So this is just the performance of the backbone itself. And it's pretty much as you'd expect, right? You do get quite a bit of spreading of the E4 450, of the UV dyes, and of the per CP conjugates. But what we did is actually generate SSMs of the 34 color backbone, as I've shown you. We generated SSMs, spillover spreading matrices, of each of the individual drop-ins, and then we subtracted those and said, how much is dropping in just one label at a time, adding to spread in other channels? Because obviously that's going to have an effect on experimental design. It's going to have an effect on data analysis, right? And so can you really plug and play these, and what are the effects of doing that? And so I'll show you that now, essentially stepping along those. And so what we're looking at here on the y-axis is actually the change in spread, right? The delta in the spillover spread matrix. And right here, I'm noting for each label that we added in on these drop-ins, right? And then I'll share some observations around, well, what does that really look like, right? And so note right here, for instance, this y-axis, because this is the largest y-axis that we have. And I've already previewed this for you because of Brilliant Blue and FTSE, Brilliant Blue 515 and FTSE. But spillover spread, when we drop in this Nova Blue 530, specifically increased for both those labels, BB 515 and FTSE, but no other dyes are affected. It essentially contributes marginal to zero spread everywhere else, right? Hence our recommendation to use Nova Blue 530 and BB 515 or FTSE. Nova Blue 610, little to no change in the spillover. Nova Blue 660, little to no change, right? And so this low impact in terms of spillover and spreading really means that they are in fact plug and play, right? Given the recommendation that we're, given the caveat of the blue recommendation. Did the same thing in the yellow. What are the differences in spillover when we drop these in one at a time? Small changes in spillover, because you can see the axis here for PE and then CF 568, still very much analyzable. Small change for PE dazzle for Nova Yellow 610. Again, what we would expect based on some of the detector, the detector layout I was showing you. Small change in spillover for PE side 5, right? And I dropped in this Nova 610. But again, note the y-axis. We're talking about very marginal changes for only one fluorophore and changing in that spread. No spread essentially added anywhere else. So I think what's important to think about is not just where does it add marginal spread, but where does it add no spread at all? And the answer is, well, everywhere else. Into the blue, into the violet, into the UV, there's nothing. So I figured it'd be important to make like a TLDR for this section, which is also a question, which is, guys, you talk about high resolution biology, what is that? Well, the answer is we've added 6 colors to this backbone panel with marginal impact on spread, except for a combination which we know is already challenging, which is BB515 FTSE. Near zero spread are added to other channels. So what exactly does that mean? Well, it means easier experimental design. Right? That's the notion of plug and play. It means higher resolution of biological populations, something I care very deeply about, right? Can you analyze this data? How are clustering algorithms going to perform on this, right? If it's crap in, crap out, and you've got a lot of spread, it doesn't matter which algorithm you're using, right? You have to have those highly resolved populations to do that type of discovery work, and hence easier data analysis, right? Because you just have better resolved populations. So Senate, do you want to pause there for questions?
I think we don't really have any questions that I haven't answered. I think we've had some interest around whether we're looking at other lasers and the conjugation kit.
Yes, awesome. All right, cool. Cool, so we also, and this is not just because this is MSKCC and it's a New York webinar, but it's related. We wanted to make this data set understandable because if you're sharing this kind of data set, you've got to make it accessible so that people can analyze it, right? And I'd also say, we're in an environment where people are talking about immunology on the street. Notably, they're 6 feet away from each other, but they're talking about immunology on the street. And so, we thought, well, how do we make this really easy to understand, sort of navigate this type of data set, right? Because we're talking about, at least based on the phenotyping that we've done where there's known populations, there's at least 32 populations, sort of baseline, if you will, in this data. Although, as we'll talk about, there's obviously populations that we're discovering that are well outside of that because we've added in a whole number of new markers, right? And maybe that can be some of the follow-up here. But what we did is create this subway plot, which I honestly wish I had created years ago when I was doing some of my deeper phenotyping. And this is actually how we're looking at the gating. And I'll map in the actual gating in a second, but this enables us to communicate and then, if you will, color code all of our populations. And so we looked at all the major cell subsets because we had this kind of plex built on top of this 34 color backbone. And then we can actually drop in and then look at, okay, what are all of our chemokine receptors? What do our Nova Yellow plots look like? What do the phenotyping markers look like? And so, yes, this is an incredibly busy plot. And the point is that this will also be shared with the data. It's also shared in the layouts that'll be with our analysis because we're sharing all of this, right? So you can actually see, and I think what's important to note here, if we're just kind of zooming along a little bit, is that we're able to pull apart CD4 and chemokine receptor-like differences off of a B cell population, right? And we're able to do that across many different populations because, again, we've dropped in these very clean fluorophores that aren't adding spread to the rest to the other phenotyping markers that we are using. So just one point on this, but I also just think kind of a nice way of thinking around, okay, it is a big data set, but let's make it navigable before we share it. The other thing, of course, is that you can do some more advanced analysis on this. And I think it would be unsurprising to you that when we run this level of experiment where you're able to ask this many phenotyping questions, that you also end up with a whole ton of, if you will, undiscovered populations, right? And I'm not gating on TC because that's a mortal sin here. what I'm showing you here is just taking all of the populations that we have in all these colors and mapping them into this TC projection, right? It was generated with OpSNE. And so you can actually see here the gray color, which is this new color that I've added in here, are the populations that we haven't gated on. So there's a huge amount of biological diversity, of course, that we're pulling apart from this deep immune phenotyping. And this is part of the reason for us to share this data, is to say, well, let's go in and essentially explore some of these clusters, figure out what some of these phenotypes look like, right? And now we're just looking at some color mapping, of course, of some of the NovaFluors, right? And it's laying out as we'd expect. We've got this CD19 population that's lighting up for the B cells, right? But we're able to see this variation in chemokine receptor and CD40, which are these non-high antigen density markers, and really drive some really, I think, beautiful discoveries out of this, right? Because we were able to add these labels in. Of course, if you have an obligatory TC plot, you have an obligatory flow cytometry analysis. That's exactly what we've done here. And again, I'd say similar story in the ability for us to pull apart some really deep biology, right? And we've really scratched the surface on this, hence the reason to share. We'll be able to pull out 18 of these meta clusters, right? And this is just it mapped into TC space. But I think there's definitely some work to do. We'd love to have people to take this data apart and say, look, we've got these new subsets here, and this is what we're able to do, or share some of our observations around panel design. Hence the whole reason, really, for sharing. And that's exactly what we are doing, and quite literally today. So we're posting up the white paper that covers how I think the other part of this is, how did we do this experiment? What was the staining? Deeper questions that you'll have around what are the materials and methods, and how do we think about creating this experiment? So we have a white paper that we're actually posting up on the website. It should be up there today. Around this. You can also email me. I'll put my emails at the end and I can send it to you. The other one is that we've actually created a GitHub resource, phitonex.github.io. I was actually just starting to upload the data, and then I realized I was out of time because we had to join this webinar, but we'll be posting the data there, as well as the FlowJo workspace that has it analyzed. So all the different visualizations that you saw here, if you want to dig in on that data and look at NovaFluors, look at any other markers on there, that'll all be available to you. And we'll also be posting it up on Flow Repository. I think for people that have known me for a while, I'm very big on sharing the data. And I think it's a great time to do that, because now we can all dig in on that and share observations. Again, be they on the NovaFluors or not, I think this is a really interesting time to think around how do we do that and think about high resolution biology. So how, right? How do we get access to these fluorophores? What's this look like? And I know, Sed, you had a question around the conjugation kit as well. And the how is this. So what we've done for these first 6 labels, and yeah, I am saying first 6 labels, hence probably the follow-up question around where else are you looking at, is we've done a CD4 test kit. And I've been a huge proponent of characterizing your instruments using CD4 test kits and SSMs for a while now. I think it's really important to do when you think around really rigorous panel design. This is no different, right? All of these are conjugated to the human SK3 antibody, and I think it's a really nice tool in thinking around how do I take this and then put it into my hyperparameter panels. We've also got a conjugation kit, and I'll actually talk a little bit more about what does that look like in terms of steps and in terms of workflow in a moment, because we've been very intentional, and frankly, we tested a huge number of conjugation kits and really found a partner that we really liked working with for a conjugation kit that was both easy and efficient and very, very rigorous around the way it was labeling these antibodies. And as someone actually asked about earlier, we currently do not offer conjugated content, but we are taking on projects for custom conjugation. So as long as you have a project where we're looking at 1 milligram or above of conjugated antibody, we'd love to hear, okay, what specificity, what label, and how can we get that into your hands? And so to spend just a moment, because I know this was a question on the conjugation kit, and I think it's also interesting because there's a couple other questions that I think were linked into that. We have a question around NGS, a question on the conjugation kit, a question around how's this all going to work? And I think it's also important because I think we're in, if you will, a new era for thinking around conjugation kits. And why is there's only a certain amount of content you can actually get access to, if you will, antibody specificity you can get access to on certain dots, right? And so you're kind of limited. And what we're doing is saying, look, you can open up this area in the spectrum that you haven't really been able to do much with in a while in the BYG space, and now you're able to multiplex in there, right? So I think there's whole new areas of content that really open up there because you can do it very clean, right? And so there's really just 3 steps in this conjugation. The first one is taking a single-stranded DNA linker and attaching it to an antibody, right? And the way that works is you add antibody, you incubate it, and then you add a quencher. And what that is doing is activating the antibody. and then putting a single-stranded linker right directly onto that antibody, right? Then we clean it up. It's pretty simple, right? Literally take out all the excess. Now you've got the antibody, which is labeled with a single-stranded DNA, right? It looks very similar to like sort of the schematics you guys have seen of an AB-seq or a triple-seq antibody, but with a unique sequence. And then what we do is actually quite literally just incubate this with phytons that off of one arm of the phyton have that conjugate oligo, right? And these bind to one another, and it's incredibly efficient. So we get over 85% yield at this step, and we've seen anywhere from 60 to 80% on this side. And you do not need to HPLC purify this, right? It's essentially you have free phyton solution, and that all washes out, right? And so you really can say, look, if you get the conjugation kit, you can be doing the types of experiments, certainly on the Aurora, but I would also add, the other platforms we talked about too, for Tesla, others, cytometers, because they all have these BYG lasers. They all have the same issues with the P and P conjugates, and be running those NovaFluor conjugated antibodies in your experiment really within a day, right? So hopefully I'll give you guys a good summary of sort of this notion of what does bright and clean mean? What's the impact of that? How do you really push the envelope in terms of consistency and stability, right? I think some data that we're showing that, honestly, we haven't seen really in our field. This notion of tunability, a brand new capability, plug and play. Hopefully have sort of shown that to you through the use of this 40 color data that we just literally plug and play these. And really in the end, the ability to discover more, right? Because it really has to be fluorescence that's designed for biology, not the other way around. Biology accommodating the fluorescence, right? And hopefully, just a bit of a new way of thinking around panel design and how you use your instruments. If you're at all interested in getting the white paper, happy to email that to you literally right now, right after the webinar. You can email me, Mike Stadnisky at Phitonex.com, or just info@Phitonex.com. Actually, this is the team in our lab, and would love to take any questions you have. And maybe I'll actually just kick it off with the first question, which is, are you looking at other laser lines? Yes. Not much to say right now on that. We're obviously very focused in on the BYG part of the spectrum for this early work. I think we've got a little more to say in terms of what we could do in BYG, but I think as you can appreciate, this approach and thinking around stacking cleanly and lowering spillover really applies across the whole spectrum, right? And we could really think about, gosh, how much easier could data analysis be when you really have spread being a thing of the past, or where you could go incredibly high plex. But oddly enough, as you increase in plex and you increase the number of NovaFluors you're using, the complication of the experimental design goes down, right? And so I think that's a very interesting, if you will, inverse correlation that I think we're going to be working. You can see that some of the things I was saying were above and beyond 40. That's certainly where we intend to go.
Okay, Mike, we got a number of good questions. So one is around the NovaBlock. What does it do?
Yeah, good question. So actually, you probably saw this earlier in my slide where we had a 4 cluster, and there was some background in that slide. So the NovaBlock is a non-protein, non-antibody-based blocking solution that is very similar to the blocking solutions that block the Cy5 and Cy7 binding to monocytes and macrophages, right? And so we deploy that for our NovaFluors as well. So the way, and correct me if I'm wrong, Seb, I think you've done a 5-minute incubation before staining.
Yes, that's correct.
That NovaBlock. And that prevents that background staining to monocytes and macrophages. So we went in and characterized that, created a proprietary block solution for that. And it's present when you stain, integrates into the workflow, and then you just stain and move on. Other than that, though, I want to point this out. All of the stability experiments I showed are, it's in PBS. There's zero other buffers. There's no other workflow changes at all.
All right. So then a question, is the single-stranded DNA, is it a covalent link to the antibody? So I don't know if you want to address the chemistry.
Yeah. Yeah, absolutely. So, and this is standard chemistry, right? So we're just using standard NHSS with chemistry to get that oligo onto the antibody. So yes, it is covalently linked to the antibody.
Yeah. And then, are there any effects of the additive present in the antibody prep? And I guess I'll try to address that one. Obviously other proteins would interfere because, it's a label. proteins, so you wouldn't want those present. There is a list that we have, so if you're interested in that, we can, look specifically at the additives, but mostly you want to make sure that the antibody is greater than 1 mg per mil, and that there aren't the proteins present. So that's what I would say.
Yeah, absolutely.
And then we've got a very good question. Let's see, we've got a question on the t-SNE plots. Did you see any differences in the t-SNE plots comparing stained cells with conventional fluor and your dyes, considering less spreading as observed with your dyes?
Yeah, it's a good. So yeah, did we observe any? So in other words, could you add in? Trying to think about the best way to answer that question. So the best way to answer that, like literally answer that question, not answer your question. So because I think it's a really interesting question. Is so essentially, could you add in terms of the number of, for instance, clusters that you could detect by flow cytometry, not the meta clusters, like the actual clusters, between the 34 color panel, and then maybe you can even do it for the plus ones, right, that we did, and the 40 color. Haven't done that yet. Need to. I think it's really interesting to think about. Yeah, because of this cleanliness, are you, for instance, getting more complexity in the underlying biology? I think that the only tough part there is like, what's the comparator? You don't have another like 40 color where there's drop-ins. There you go, another color. So I think maybe a more fair comparison would be almost like the Fortes experiment, where you've got, that stack in the but it's the same number of fluorophores in both. But same specificities. You know what I mean? And then saying, okay, look, is that notion of high resolution biology, are you actually able to get out, for instance, on an unsupervised basis, more clusters, out of the same algorithm, same set? Happy to talk about suggestions on that one.
Yeah, and I think just to follow up on what Mike was saying, that's one of the things we probably want to look at. I don't know what's going on there.
Yeah, sounds like someone's in a ballpark. That's fantastic.
So anyway, I think that those are the main questions. If anyone else has any questions, feel free to. Oh, and this question: are we going to share our presentation? So I believe that Kathy and Rui will be sharing that. Yeah, I'll pass this back over to Rui.
Yes, thank you, Mike, thank you, Sid. This was a great presentation, and I'm really excited. We were just talking about that earlier. These are exciting times. The community, the scientific community, is starting to look at all these huge panels, and bringing this kind of technology and solutions into improving panel design is really exciting. And so we're really looking forward for more fluorochromes coming out of Phitonex. I want to just say that yes, this presentation will be available in our website. So if you want to go back and listen to it, of course, feel free to reach out to Mike and Phitonex if you have any questions. I also want to say that we're going to be working with Phitonex to get some to start testing these dyes, because again, we're really excited with this opportunity, and so for the users of MSK, reach out to us if you're interested in using these in your panel. We'd be more than happy to help you out. So with all this, I'd just like to thank you again, guys, for this wonderful presentation, and hope to see you guys soon.
Sounds good. Thank you, Rui. Thank you, guys.
Okay, great. Keep safe.